The goal of this project is to retrofit a Bowler & Chivin 16-inch telescope mount. The 1960s-era analog drive system will be removed and modernized with brushless DC motors, industrial-grade control hardware, and computerized pointing software. A large roboticized telescope is a complex system, so this project has been divided into 5 major components: a user computer, a master controller, motor control, active tracking, and safety. In the first phase of the project, a proof of concept was developed using stepper motors, UART communications, and a basic motor control algorithm written for a TI microcontroller. With Phase A successfully completed and tested, work is being scaled up to hardware that will ultimately drive the telescope. The components previously tested have been upgraded and are now being developed in their final form. In this video, we will talk about the current state of each major subsystem and discuss the work that still remains.
The master control subsystem translates information from the user computer and handles the motion and safety of the telescope mount. This subsystem is comprised of 3 parts: the EtherCAT master computer, the EtherCAT terminals, and communications to the user computer. EtherCAT is a type of control technology that relays information between the master computer and the terminals with very short update times. In this project, EtherCAT control sends motor commands to the output terminals and receives encoder information from the input terminals. These terminals are connected to the motor controllers and encoders respectively. Information from limit switches are also received by the input terminals and relayed to the master computer. The EtherCAT master computer has 3 jobs: translate the coordinate information from the user computer into motion instructions for the motor control subsystem, translate the encoder information from the telescope mount into position information for the user computer, and ensure the telescope mount remains within safe bounds using information from the limit switches. The EtherCAT master computer must also stop the telescope mount if an emergency is triggered by the user on the user computer. Currently, the master control subsystem is connected to the user computer with ADS, and the EtherCAT master computer can send and receive signals to and from the EtherCAT terminals. To test the communication between the user computer and the master control subsystem, the user computer sends a message to the EtherCAT master over the ADS port. The master computer debugger shows the received message and updates a variable that the user computer is monitoring. If the user computer receives the updated variable, the test passes. To test the input signals from the EtherCAT terminals to the EtherCAT master computer, active signals are connected to the EtherCAT terminals. A laptop running a debugger interface connects to the master computer and monitors the terminals, and if the signal is displayed by the debugger, the test passes.
Hello, I'm Philip Nagy, and this is the Active Tracking Subsystem for Aggie Telescope. The Active Tracking Subsystem is in place to improve tracking accuracy and correct for periodic error that stems from the drive system. The Active Tracking utilizes the CCD to feed in video, which is then processed within MATLAB, and stellar object points are denoted, labeled, and saved. This saved data can determine if the tracking is drifting out of alignment, and from this data, motor commands can be generated and sent to the user computer and EtherCAT subsystem to be processed by the motors. The system requires the use of a CCD and a computer with MATLAB with the Image Acquisition Toolbox, Signal Processing Toolbox, and their respective add-ons. The computer which tracking is functioning on must have an Intel or AMD x86 processor and the support of at least 2 GB of RAM. These requirements ruled out platforms such as the Raspberry Pi 2, which only have 1 GB of RAM and support an ARM processor. The program requirements are such: be able to take in CCD video feed and select the number of frames per second to run at, track stellar objects and utilize centroiding to locate the exact center of each object to accurately determine the position within the frame, The program then must save the frames and location data within a text file. This location data is then used to characterize error and create motor commands that are sent via EtherCAT to correct tracking error. In this test, the tracking portion of the active tracking subsystem will be tested, while the generation of positional corrections will come next. The test utilizes the rear-facing camera on a Surface Pro 3 in lieu of the CCD for the telescope. The camera is pointed at a predominantly neutral background to serve as a non-interfering background, and the video stream is observed prior to running the program to ensure the initial conditions are acceptable. The program is then run and information requested from the user, such as whether the mask has been initialized and set, as well as how long the program is going to run for. The user sets up the mask and applies it to the video stream, which cuts down on extraneous information in the frame. The code is then run, and red circular and crescent-shaped blocks are used to test the recognition and centroiding. The center of each object is denoted by the plus sign, which is determined via the centroiding algorithm. Max and minimum object sizes are set and is demonstrated by having different size objects at the same distance, where the program will recognize one, yet not the other. Lastly, the frame grabs and location data per frame are saved within their respective folders.
The user computer is an astronomer's primary means of controlling the telescope. In the proof of concept, a simple Java user interface was created and used to control the prototype drive system. The final version of the telescope interface will be written in C#. This is primarily because the EtherCAT ADS system is designed with a software interface for C# programs. Though the user interface is being redesigned, it already has all of the functionality of the prototype, and new features are being added every week. The primary interface screen is a status display for the telescope system, with command and location data provided along the top and pointing information shown at the bottom. The large display in the center currently shows a picture of space, but this will be replaced with a map showing objects where the telescope is pointing. There is a row of buttons along the top of the window that allow users to interact with the telescope. Currently, the user can bring up the virtual paddle and object database helper windows. The virtual paddle simply lets a user manually control the telescope, useful for alignments and testing. The object database brings up an interface that collects to the Simbad online astronomical database. By searching for an object, pointing coordinates are looked up and an image is downloaded from the Sloan Digital Sky Survey online image database. Additionally, a user may search for objects in a certain region of the sky through the By Coordinates tab. As objects are looked up, they are entered into a local SQL database that stores object names and coordinates. This allows users to point and track objects even when there is no internet connection. Being a piece of software, testing is not as straightforward as it is with hardware. Unit tests are being run, searching for edge cases that cause the program to throw errors. Once the master computer is integrated with the user interface, test scenarios will be run to ensure that the interface operates properly under unlikely and important conditions, such as an emergency stop or power loss. Additionally, the program is being passed on to the intended users to verify that it satisfies their requirements. Being a large, complex project, there is still a great deal of work that needs to be done before the telescope is complete. The motors and motor controller hardware has just come in, so work is now being done to test and verify this hardware before it is integrated with the master controller. The active tracking feedback software can then be added to the loop to ensure that it tells the telescope how to track properly. The user interface will continue to have important features added, with the highest priority currently being given to adding ADS functionality so it can communicate with the master controller. Finally, the telescope will be assembled and tested before the final product is turned over to the Texas A&M Astronomy Department. Thank you for taking the time to watch our video. The task of refitting a full-size telescope is both extremely challenging and highly rewarding. The members of Team Telescope are proud of the work that has been accomplished so far and continue to work toward our goal with a great deal of excitement and enthusiasm. We look forward to the coming weeks when we will be able to show off the fruits of our labor at Demo Day. We'll see you there.